Hello dear students, as you all know we are doing chapter number 1. Today we are going to do 6th part of the lecture series, and today we'll study area vector, the first thing, then electric flux, and today we are going to cover a very important topic for your board examination, and that topic is Gauss law. Then after, proof of Gauss law. Although it is a laws are not proved, but it is a kind of verification for a point charge. Okay, and then after we'll solve some numericals which are based on electric flux and Gauss law. Okay, so let us start. The first thing we are going to study today is area vector. You must have learnt in class 11th that area is considered to be a scalar quantity, but here I am telling you it is a vector quantity. A vector quantity must have direction. We must associate area of a surface with a particular direction. How it is being associated, let us see. We define area vector by the area vector of a surface is a vector whose magnitude is equal to area of the surface, obviously, and it is directed along the perpendicular to the surface. Okay, the direction of the area vector is perpendicular to the surface. Okay, it is denoted by a vector or s vector, and it is equal to a n cap, where n cap is the unit vector in the direction perpendicular to the area vector. Okay, now let us try to understand by a diagram. Suppose this is an area vector which is kept horizontal, it is a plane surface. So its area can be calculated by multiplying length and breadth because it is in rectangle shape. It is kept horizontal. Just try to see it in 3D. So it is a rectangle kept horizontal. So let its area will be length into breadth, but its direction will be upward. So we denote area vector as a vector, and the direction of n cap will be in this direction. Is it clear? But there can be a doubt because for a plane surface we have two directions of perpendiculars. The black one can also be a perpendicular in this direction, and green one can also be a perpendicular in this direction. In which direction the area vector should be taken? The answer is you can take in any direction, but remember that if one you consider as n cap, then other it would be minus n cap. Is it clear? So this is how we define area vector. Now suppose if the surface is not plane, it is curved, then what we do? Then in that case, if the surface is three-dimensional, what we consider an elementary area ds on the surface, and the direction of this elementary area vector is along the local normal. Local normal means normal at that very elementary area of the surface at the where the elementary area is chosen as shown. Okay, now with the help of a diagram let us understand this. Suppose we take a hemisphere. So on the hemisphere what we do, we take an elementary area, let this elementary area be ds, then its direction will be perpendicular outward from the surface. So here the direction of elementary area will be, and it is denoted by ds vector is equal to ds into n cap. ds is the magnitude of elementary area, and n cap is the direction of that unit direction of that elementary area. Okay, I was telling you about ds and n, so let us write it about also. Here the n cap is the unit vector along the normal outward to the elementary area element ds. Okay, now let us move ahead and let us study about electric flux. What is electric flux? So basically electric flux is the measure of electric field. Suppose a surface is there, a surface is in a space where electric field is already present. So how much electric field is passing through the surface, it is what we call electric flux. Okay, so definition of electric flux is given by, Just try to understand first of all with a diagram. Suppose a smaller elementary circular disk is there and it is present in an area where E vector is present. Then how much electric field which is passing through the disk? Whole of the disk, through the whole of the disk electric field is passing. At one point the electric field is E, then whole area the electric field will be. So what we write? We write the direction of area vector. For the sake of convenience, let us take it in the direction of E only. So for this we can write phi is equal to E into A. But if this area is tilt like this way, then its area vector is going upward. Now it is making an angle theta with the electric field. Now what we need to understand here, that whole of the electric field is not passing through the area. Some of the electric field above and some of the electric field down will be skipped. So how much electric field is passing this time? So what we are going to do, we are dividing the area into two components. One is A sine theta, another is A cos theta. Here that the component which is along the electric field, which will be taken in consideration, because here the area vector along the electric field is multiplied. The component of area vector along the electric field, which is A cos theta, is multiplied with E. So in this case the flux is given by phi is equal to Ea cos theta, or we can write E vector dot A vector. So this will be the formula for the electric flux. From here, if we want to make a definition, to what we say that electric flux through a surface is defined as the measure of electric field lines passing through the surface normally. Mathematically, it is defined as the scalar product of electric field and the area through which field is passing. Normal electric field which are passing through the surface. Normal means perpendicular to the surface. Just see here, all the electric field lines are perpendicular to the surface. Here they are not. So what we do, we take components. A cos theta is along the electric field, and that's why we have considered A cos theta, because through A cos theta the electric field is passing normally. Okay, mathematically what we write? Okay, mathematically I have written the formula here, phi is equal to E vector dot A vector, but the story changes when the surface is not plane, it is curved. Then what we do, we take elementary area, and through that elementary area we calculate flux. So suppose if we take an elementary area dA, then electric flux through dA is d phi is equal to A vector dot dA vector. For total flux, what we do, we integrate d phi, and for that we get surface integration of E vector dot dA vector. This is a different kind of integration which is called surface integration, and it is basically what, when we integrate it, so we integrate the surface area element, and what we get in answer, we get the total surface area. Okay, so that dA, the area chosen is so well, so that E dot dA, okay, can be integrated and we can get the value of flux. There are some more important information about flux. Let us see that. The first thing is, it is a scalar quantity. Okay, obviously it is a scalar product of E vector and A vector, so obviously it is a scalar quantity. Second thing is, its unit is Newton meter square per coulomb, and its dimension is ml3 t minus 3 a minus 1. Okay, the third point is, the value of phi does not depend upon the dimensions, does not depend upon the distribution of charges and distance between them inside the closed surface. Okay, how the charges are being distributed in the surface, it does not, the phi does not depend upon them. And the next one is, the outward flux through a surface is positive, whereas the inward flux is negative. Okay, there is a sign convention. What we consider the outward flux as positive and the inward flux as negative. Okay, so this is what the whole things are about electric flux. Now electric flux, why we study electric flux and area vector? Actually, these are important tools to calculate electric field due to a configuration. Now this chapter is all about finding electric field. Okay, in the last lecture we have studied electric field due to an infinite wire. If some charges are given on the vertices of a triangle or a square, Then also we determined the value of electric field at the centroid or center respective to the question. So here is one more method by using Gauss law, and for understanding Gauss law we must understand electric flux and area vector. So basically electric field flux is what? It is the measure of electric field which passing through a surface normally. And what is area vector? Area vector is a vector whose magnitude is area and whose direction is perpendicular to the surface. And if it is a 3D surface, then perpendicular outward from the surface. Okay. Now let us start Gauss law. What is Gauss law and what it does? So Gauss law basically relates the total flux of an electric field through a closed surface, total flux of an electric field through a closed surface to the net charge enclosed by that surface. Means electric flux and the charge which is enclosed by the surface. Its statement is given by the net electric flux passing through a surface is 1 upon epsilon naught times the total charge enclosed by the surface. That is, mathematical form is phi is equal to integration of d phi is equal to integration of E vector dot dA vector. It is the definition of electric flux only. From Gauss law we can write Q enclosed upon epsilon naught. So for a point charge we are going to verify it. Let us see. What we have to prove? We have to prove that phi is equal to integration of d phi is equal to surface integration of E vector dot dA vector is equal to Q enclosed upon epsilon naught. Okay. Let us prove this. So what we do? We are going to take a point charge which is plus Q. And what I'm going to do, I'm going to take a Gaussian surface around it. And that Gaussian surface should be a spherical one. Why I have taken a sphere, why I have not taken the cube, why I have not taken the cuboid, why I have not taken the cylinder or any other shape or hemisphere, anything. Okay. For that thing, I'll tell you during the proof. Okay. Now let us start the proof. What I'm going to do, just see the radius of this sphere is capital R. At certain point, I'm taking a smaller area element. The area element makes an angle. Outward the sphere it is ds, and the electric field will be in the same direction, and it is E in the same direction. That is, E and ds are same direction. That's why the angle made between them is 0. This is the factor why I have taken the sphere. Suppose if I have taken a cube, if I would have taken a cube, then the direction of area vector and the direction of electric field is entirely different at every point. And we cannot generalize that E dot ds, because E dot ds is equal to E ds cos theta. And if angle between E and ds changes at every point of a taken surface, then what happens? We cannot integrate it. Is it clear? That's why it is taken as sphere, so that direction of electric field and direction of area vector should always remain in same direction. So let us prove it mathematically. We have phi is equal to surface integration of E ds, E vector dot ds vector. It is the definition only. Now that E ds is expanded and it is written E ds cos 0 because they are in same direction. The value of cos 0 is 1, and E is, since we have taken a sphere and the distance and the electric field is a function of distance only. Okay, so at the surface of the sphere the electric field remains constant. E can be taken out, surface integration of ds, and surface integration of ds becomes 4 pi r square. The value of electric field is kq upon r square into 4 pi r square. The value of k is 1 upon 4 pi epsilon naught into r square. Now 4 pi r square will be cancelled out, and in place of phi we are going to have q upon epsilon naught, which we have to prove. So this is the proof of Gauss law. It is very easy, and actually I am telling you it is not the proof, it is a kind of verification only, because there are no proof for the laws. Laws are some standard experimental results which have no proof. Is it clear? Okay, I hope it is very easy, and from in every board examination we have some questions from the Gauss law. So you must understand the law, and by practice you will get that. Okay. Now some important points related to Gauss law. The very first point is flux through a Gaussian surface is independent of its shape and size. So instead of, if we would have taken a cube, then also the flux will be q upon epsilon naught. if we would have taken a cylinder, then also the flux would be q upon epsilon naught. Means the direction of the shape of the Gaussian surface is not a thing to be considered when we are looking to the flux. Is it clear? And obviously the size also. In some time in the board examination it is being asked, if the radius of the sphere is become twice, then will be the change in the flux? The answer is no change, because it does not depend on the size. Second thing is, flux through a Gaussian surface depends only on the charge present inside the Gaussian surface, not on the surface, and not charges present outside the surface. The flux at a point depends only on the charges inside the surface. Okay. Third point is, flux through a Gaussian surface is independent of position of charge inside the Gaussian surface. It does not matter whether the charge is just inside the surface or it is basically at the center, or it is somewhere very lost inside the surface. If the charge is present inside the Gaussian surface, then flux will be the same irrespective of the position of the charge. Fourth point is, the electric field intensity at the Gaussian surface is due to the all charges present inside, all charges present. This point is different from the point number 3. Point number 3 that says that electric flux depends on the charge enclosed only, whereas this point tells us that electric field intensity at the Gaussian surface is due to all charges, whether it is inside or outside. And the electric field and electric flux, they are two different things. Okay, so when you calculate electric field, be very careful. When you calculate flux, be very careful. Fifth point is, in a closed incoming flux, in a closed surface, the incoming flux is taken negative while outgoing flux is taken positive, as I have told you earlier also this point. And the last point, and very important point, conceptual one, is, in a Gaussian surface, phi is equal to 0 does not imply E is equal to 0. If through a Gaussian surface electric flux is 0, it does not tell that electric field will also be 0. Phi is equal to 0 does not imply E is equal to 0. But somewhere if E is equal to 0, then at that point phi will be 0. Is it clear? So this is what for 6 we'll do some examples also when I'll teach electric dipole. Till now we have not done electric dipole. When I teach electric dipole, we'll discuss this point. Okay, then this point will be clear. Now let us move ahead, and now we are going to solve some questions based on Gauss law and electric flux. The first question is, and question is quite larger, the electric field is uniform and in the positive x direction for the positive x, and is uniform at the same magnitude but in the negative x direction for negative x. It is given that, what is being given that, so it is so confusing, the line is so confusing. Actually it is given that the electric field is constant, but in the positive x direction, somewhere here, the electric field is in this direction, here only. In the negative x direction, electric field is in this direction. Okay, but the electric field value remains constant, only the direction changes. Now mathematical statement is given, E is equal to 200 I cap, Newton per coulomb for x is greater than 0, E is equal to minus 200 I cap, Newton per coulomb for x is less than 0. Okay, that is the same thing. A right circular cylinder of length 20 cm, radius 5 cm has its center, the origin, and its axis along the x, so that the one face is at x is equal to 10 cm and the other is x is equal to minus 10 cm. The length of the cylinder will be 20 cm. Now questions are, what is the net flux, net outward flux through each flat face? What is the flux through the side of the cylinder? What is the net flux through the cylinder? What is the net charge inside the cylinder? This question is there in the NCERT also. I think in NCERT exemplar or NCERT somewhere, but this question belongs to NCERT. Diagrams tell me that. Okay. Now let us solve this one. So this diagram has been given. What I'm going to do, I'm going to take surfaces in the diagram. Just see, here I have taken S1, this flat surface, S2, this flat surface, and the curved surface is S3, right? Now let us solve the first one. The first one question was कि what is the net flux, outgoing flux through the each flat surface. So first of all we'll solve for S1. Net flux through the S1 is given by phi1 is equal to E vector dot A vector. E vector is 200 I cap. A vector is pi r square into I cap. I dot I becomes 1. When we solve this, we are going to have phi1 is equal to 0.5 pi Newton meter square per coulomb. Okay. Same goes with S2 also. Same calculation, only it will be the phi2. Area is same, electric field is same, everything is same. Answer will be also the same. These are the outward flux through the flat surfaces. Second question is what is the net flux through the cylinder? Okay, second question was what is the net flux through the cylinder? No, sorry, what is the flux through the side of the cylinder? Means curved side. So for the curved side, if you can see here, that area vector makes an angle 90 degree with the electric field, and because of that E delta S cos E delta S, when it is expanded, it becomes cos 90. Value of cos 90 is 0, therefore d phi will be 0, and if d phi is 0, then total curved surface is 0 only. Okay, the value of phi 3 will be 0. Now the net outward flux, obviously the phi1 and phi2 both are outward flux, we'll add them, and then we are going to have pi Newton meter square per coulomb. And the last question is what is the net charge enclosed by the cylinder? Then answer is, since Q is equal to flux is equal to Q upon epsilon naught, Q is equal to what? Flux into epsilon naught. The value of flux we have calculated, it is pi. The value of epsilon naught is 8.85 into 10 to the power minus 12. When we multiply, we'll get the value of Q. It is 2.78 into 10 to the power minus 11 coulomb. This will be our final answer. Okay, question is very easy, only it is lengthy and its diagram is so confusing. Sometimes the students gets confused. They start calculating curved surface area, flat surface area, everything. But calculate only those things which are required for the solution. Okay, don't go for longer calculations and everything. Okay. Let us solve the next. Next question is, the electric field components of a figure shown, Ex vector is equal to Ax to the power half I cap, Ey is equal to Ez is equal to 0, where alpha is equal to 100 Newton per coulomb per meter. Calculate the charge within the cube. Assume that A is equal to 0.1 meter. Where is the diagram? Here it is. Okay, this is the diagram given in the question. One cube is there, and its first side is at a distance A from the origin. Okay, electric field is given alpha x to the power half, and value of alpha is given 100 Newton per coulomb per meter. Okay, A is given 0.1 meter, and what we have been asked, calculate the charge within the cube. If we calculate the flux, then charge will be given by Q is equal to flux into epsilon naught. First of all, we will calculate the flux. Okay. Now I'm going to make two surfaces here. Just see, one surface is S1, this surface, this flat surface, which is the right side of the image, right side of the cube, and one more surface which is S2, which is left side. Okay. The direction of area vector through S1 is A vector, and direction of electric field is along it only. The direction of area vector of S2 is just opposite, and it's here the direction of electric field is here in this direction. So area vector and electric field are in opposite directions, right? Rest 6 faces, one which is at the front, one which is at the top, one which is at the back, and one which is at the bottom. Through all these 4 surfaces, let me repeat again, one which is at the front, one which is at the top, one which is at the back, and one which is at the bottom. Through these 4 surfaces, the electric field will become 0, because the area vector of these surfaces makes an angle 90 degree with the electric field. Okay. So net electric flux through the surface S1 is given by S1. Here I am telling about this area. Okay, electric field and area vector are in same direction. So phi1 is going to be E vector dot A vector. Now the value of E, value of alpha, it remains same. But just see, from the origin this surface is at 2a distance. Then in place of x we write 2a to the power 1 by 2 I cap. Area is a square into I cap. I dot I will become 1 and this will become alpha 2 a square and a will become a cube to the power 1 by 2. Okay, is it clear? Is it clear? Power 3 by 2 it will be a 5 by 2. 2 plus 1 by 2, I think this should be a to the power 5. Okay, there's a mistake, please make it correct. It should be a to the power 5. Accordingly the calculation will change. Okay, this assume that 2a to the power it should be 5 to the power 1 by 2. Now we'll put the value of a, put it 5 power and we'll solve it. Is it clear? Please change the calculation, try to understand the method. Calculation I have done wrong. Okay, you make it correct. Is it clear? So the phi 1 value is given. Same goes with S2, but in the S2 the A vector and electric field are in opposite direction, and therefore we have phi 2 is equal to E vector dot A vector. Same goes here. Here the value of a cube, it is written at the bottom of this red spot. It should be a to the power 5. Okay, it should be a to the power 5. If you put the values, then accordingly it will be solved. And now just try to understand the method what we have to do. Okay, value of phi 1 you want to calculate, it will be calculated like that. Only what a mistake I have done, 1a square should also be multiplied, right? 1a square is missing. So just multiply this equation by 0.25, sorry 0.01, it will become 0.125 root 2, and here also it will become 0.125, right? Now net flux will be, since this flux comes out to be negative. Why is it so? Because here the area vector and electric field are in opposite direction. So for the value of phi is like that, and then after net enclosed charge is given by Q is equal to phi epsilon naught. We'll put the value and we'll get the result. Please try to understand the method. Okay, somewhere the calculation mistake is there, please rectify that. Okay, let us move to the next question. Next question is, a point charge plus 10 microcoulomb is at a distance 5 cm directly above the center of a square as shown in the figure. What is the magnitude of the electric flux through the square? Okay, what is given, a square is there, and from the center of the square 5 cm above it one charge is there. You need to find out what is the flux through the square. This question is very easy if you see the solution in symmetry, right? What we do, we make a cube, we assume a cube, and the side of the cube is 10 cm only as it is there, and at the height 5 cm one charge is there. So for this cube, this charge is at the center, so that the net flux through the cube will be phi is equal to, if phi is the total flux through the cube, then just try to understand the cube has 6 faces, and till 6 faces the total flux is phi. What will be the flux through the one face only, which is at the bottom? Is it clear? So net flux through the surface is given by phi dash is equal to 1 upon 6 into phi, or phi, the value of phi is q upon epsilon naught. So basically the answer is q upon 6 epsilon naught. Now it is all about putting the values and getting the result. So it will be 1 by 6 into 10 to the power minus 5 upon 8.854 into 10 to the power minus 12. When we solve it, we are going to get result. Okay, question is very easy. There is nothing much to explain in this question. The same type of questions one can be more there, like what is the magnitude of electric flux through the hemisphere as shown in the figure. It is a half of the sphere. What we do, we'll make the whole sphere, and through the whole sphere, if the flux is given by phi, so through the hemisphere the flux is given by phi dash is equal to phi by 2, because upper surface is not there. Okay, so it will be phi dash is equal to phi by 2. We are going to have phi dash is equal to q upon 2 epsilon naught. Same one more question is there through the symmetry, and it is, one charge is present at the corner of a cube, what is the net flux through the shaded face of the cube? Like here it is the shaded face. Through one face only we have to tell. This question is different from the previous one where the charge was present at the center. Here the charge is present at one particular corner, and what we have to find out, we have to find out the flux through this face only. Now let us try to understand how this question was solved. Now I am going to draw a geometry. You'll be able to understand from the diagram. Just see this cube basically, which is given here. It is a cube number 1. I put a cube number 2 just behind it, 3 here, 4 here, and at the bottom same 4 is cubes. Then what will happen? The side of the cube will be just twice. We have a cube now, and the side of this cube is twice of the side of this cube. Through the bigger cube, the total flux, if it is phi, then there are 8 cubes. So what is the flux through one cube? If phi be the total flux through the 8 cubes, then phi dash be the flux through the given cube, then phi dash is equal to phi by 8. Okay? Because it will become q upon 8 epsilon naught. Now for one cube only, there are 3 faces which are in contact with the charge, and 3 faces which are at the far end from the charge. So this flux will be divided into 3 parts, because the surfaces which are in contact with the charge, like this surface, bottom surface, and the surface which is at the back, net flux through these 3 surfaces will be 0. Okay? So we have a surface which is at the top, we have a surface which is shaded one, and we have one surface which is at the front. The total flux will be divided into 3 surfaces, and therefore the answer will be phi double dash is equal to 1 by 3 of q upon 8 epsilon naught, and it will become q upon 24 epsilon naught. I have made a different diagram so that you can understand. Like suppose at D the charge is there, then the face ADHE, the flux will be 0. The flux through ABCD will be 0. The flux through DCGH is 0 because they contain the charge. But the flux through ABFE, BFGC and EFGH, these 3 surfaces, flux will be divided in equally. Total flux through the cube is q upon 8 epsilon naught through one phase. The flux will be 1 by 3 of that, and then the answer is q upon 24 epsilon naught. Okay, so this is what we have to study today. This is what till what we have to study today. Tomorrow we are going to do some applications of Gaussian law. Okay, and then after we'll move to electric dipole. So this is all for the day. Thank you.